Let's begin. Lecture 2 of our course. Today's topics are, we'll revisit a few aspects of the C to D versus A to D. Again, this is a familiar topic, but I thought I just wanted to mention one more time. Dirac delta, everyone has studied it probably in your networks and systems course, but worth revisiting the properties because that is important. We are going to be going back and forth from the analog domain to the discrete time domain, continuous time domain. Sampling, our discussion in today's class was going to focus primarily on the frequency domain. We already looked at time domain sampling, and time domain is the uniform sampling. And we will also see how the Nyquist criterion comes from the frequency domain interpretation as well. So, that is another part of today's discussion. What if Nyquist criterion is not satisfied? Then we have the problem of aliasing. How do you ensure that aliasing is not present? We use something called the anti-aliasing filter. So, why the anti-aliasing filter comes and how multi-rate signal processing helps you work with the anti-aliasing filter. So, that is a very key takeaway from today's lecture. And then of course, we are always interested in the final outcome. In the discrete, in DSP very often our entire processing starts in the discrete domain, you do the processing and then you do the output in the discrete time domain. You really do not worry about converting it back into an analog signal. In our case, very often we do want to, in the application that we are looking at, we are interested in the reconstruction process. So, what is the reconstruction filter, what is an ideal reconstruction filter, approximations of ideal reconstruction filter, and then also in the course of today's lecture a few interesting examples as well. So, let us begin. As always, feel free to ask questions. As I mentioned in the last class, I will repeat the question because it has to be audible for the recording purposes. So, by and large, when we say that we want to sample a signal, the underlying assumption is that the signal is band limited by its inherent property. Alternatively, I have to make it band limited. So, one or the two, either it is band limited or it has to be made band limited, then we apply the Nyquist theorem. Nyquist theorem says that I must be greater than 2 times the band limiting, the bandwidth of the signal. So, keep that picture in mind that the band limiting process, so the band limited property either has to be inherent or it has to be sort of forced upon it. Right? Or it has to be created via filtering. Okay, that's going to be important element in what we will discuss today. Okay, so then the next aspect of it is the differences between A to D and C to D system. So, this is a C to D, continuous time to discrete time. This is an A to D. So, can you link the A to D to the C to D? What is the part that takes you from here to here? A quantizer. So, basically each of these samples, instead of being represented with infinite precision, do have finite levels. So, in other words, you could think of a C to D block followed by a quantizer that gives you the effectively the A to D operation. Okay. Okay. So, this is the point that we wanted to mention. So, keep in mind that here we do have a discrete, here we have continuous amplitude in the discrete domain. we do not have any loss of information due to quantization. Here it is discrete amplitudes, discrete amplitudes. The minute you have discrete amplitudes, you have lost some information. So that is a very important element. So let me just spend a few minutes on this. Again, this figure is from the last lecture, highlighting the fact that basically we are talking about uniform sampling. Throughout this course, the sampling is going to be uniform. Unless we specify, we are talking about a C to D converter, not a quantization part. Therefore, that is an important element. We assume that there is infinite precision. Let me just mention one aspect that I think is important for us to keep in mind. Okay, so when we have a quantized signal or a discretized signal, so if the samples are quantized, then we actually represent it in terms of the original signal plus some impairment or noise. So it is the original signal plus quantization noise, It is very important that the reason we keep emphasizing that we are talking about a C to D is that we really do not want to at this point focus on quantization noise, because if you talk about the quantization noise, quantization noise, then we can see that there is a signal power and there is a quantization noise power. Okay, there is quantization noise power. So the minute you start quantizing, you have to then also keep in mind there is a signal to quantization noise ratio, and the whole subject of A to D is to achieve as high an SQNR as possible. So that is a branch of study that has a important elements by itself. However, multirate DSP can play a part in reducing SQNR. So multirate DSP can reduce SQNR. That part we are interested in. Okay, but by and large, since our focus is on the multirate aspects, except when we are studying about the enhancement of SQNR using the multirate processing, the rest of the time we are more or less looking at it from a scenario where quantization noise is not the main aspect. Okay, so given that picture, then we can now say that the C to D, that is what we are focusing on, is going to take the continuous time signal, multiply it by a train of impulses as we talked about yesterday. The spacing between these impulses is going to determine how finely I will sample the continuous time signal. So here are some alternate schemes. So this is a scheme where I have a higher sampling rate because my sampling period has been reduced, and of course if I go the other direction, I will get the opposite result, lower sampling rate. Okay, so this is the starting point. So let us spend a few minutes on the Dirac delta. Again, this would be something that I believe most of you are familiar with, but it is important for us to highlight the properties, and therefore we would like to. So Dirac delta of t is a very unique function. Again, each of the branches of study of who use the Dirac delta have their own perspective on it. There is a mathematics perspective, there is a physics perspective, there is also the engineering perspective. So, I will give you the electrical engineering perspective. So, we look at it as a function that is not that basically is equal to 0 everywhere other than t equal to 0. Okay, it is equal to 0 everywhere, but it is also undefined at t equal to 0. So, it is a function that has to be specified or defined by means of its properties, because the definition itself says that there is something undefined about the function at t equal to 0. So, the ways in which we define the Dirac delta are by a series of properties, and basically we will use two properties, the sampling property and the area property. So, the area property or the property number 1, if I integrate p to q delta of tau d tau, that is I integrate the Dirac delta where p and q are on alternate sides of the 0 of the origin. Okay. So, assuming that the period of integration is on either side of where the delta actually occurs, then this is equal to 1. Okay. And there are several variants of this. One variant that I am sure you would have seen is minus infinity to t delta of tau d tau. Basically, it is the same integral property. If I do this, then what we get is actually u of t, the unit step. Okay. So, for every t you will get which is t, where t is greater than 0, you will get a unit amplitude, and therefore, that becomes the unit step. And interestingly, we also note that any scaling of this delta also scales the output. So, it does have a useful property, and that is very important for us, because we are sampling a continuous time signal. It has got an infinite levels in terms of amplitude. So, the delta function preserves the amplitude of the signal that it is sampling. So, this is property 1. Property 2. Property 2 is the this is the unit area property. Unit area property. The second one is the one that we are actually using, that is the sampling property. Sampling property is sometimes also referred to as the sifting property, but for us, since we are actually talking about sampling, sampling is the term that we will use, sampling property. Okay. So, x of t multiplied by delta of t basically kills, x of t is some function, continuous time function, kills the function everywhere except at x of 0. So, this is equal to x of 0 times delta of t. Okay. So, it actually retains the Dirac delta property, but it is scaled by the function at x of 0. And similarly, if you were to apply multiply x of t with delta of t minus tau naught, this would sample the function at x of tau naught, again multiplied by delta of t. Okay. This is a very, very useful property. Again, this may be very elementary because you have already studied it, but this is important, that because sometimes when you study the sampling property, it is not stated in terms of this, it is actually stated in terms of the sampling property combined with the integral property. So, basically this and this mean the same thing. You may have seen it that the sampling property is defined as minus infinity to infinity x of tau del tau d tau, and this is equal to, what is this? You would have studied this, x of 0, because x of 0 delta of t, if I integrate it from minus infinity, the delta of x of 0 is a constant that comes out, integral minus infinity infinity of delta Dirac delta is equal. So again, you may have seen it in this form, but what we are interested in is the sampling property that the Dirac delta preserves. Of course, the variation of this one is also that minus infinity to infinity x of tau delta of tau minus tau naught d tau is equal to x of tau naught. Okay, so basically either way there is a certain property of the Dirac delta that we need and we are utilizing. Okay, so now we will quickly develop the view of the sampling process. So let me just refresh your mind. Xc of t multiplied by s of t is the sampled signal. So that is the signal that we are going to be working with. The sampled signal xs of t is equal to xc of t multiplied by s of t, where s of t is the periodic train of Dirac deltas, summation n equal to minus infinity to infinity delta of t minus nts, where ts is the sampling period, and so basically these Dirac deltas are spaced at that point. Okay. Now would like to get the representation, the time domain representation is straightforward. So basically what is happening is that the sampled signal x of n is xc of nts, where n is a number that is n is equal to 0 plus minus 1 plus minus 2. So time domain is very straightforward. So basically we are sampling the continuous time signal, but the frequency domain is also very insightful. So that is what we are going to be looking at. So we would like to get the Fourier transform of this signal, Fourier transform. So xs of j omega. So basically we want to get the Fourier transform of xc of t multiplied by s of t. It is multiplication in the time domain. So in the frequency domain it is 1 by 2 pi the Fourier transform of xc of j omega, that is the spectrum of the continuous time signal, which has been assumed to be either band limited to begin with or forced to be band limited via filtering, convolution with s of j omega. So the input spectrum, this is already given to us. This is already given, and this is what we want to compute. And again, this is a computation that I am sure you would have done in one of the earlier courses, networks and systems, or one of the other courses, but it is important for us. So just spend a few minutes just to get the relevant representation. So I want to get the Fourier transform of s of t. So s of t is a signal which we have already drawn. It is a train of Dirac deltas which are spaced at Ts, 2Ts, minus Ts and so forth. Okay. And because of its periodic property, it lends itself to a Fourier series representation. So first step would be the computation of the Fourier series coefficient, 1 by Ts integral minus Ts by 2 to Ts by 2 delta of t e power minus j k omega naught t dt, where omega naught is my fundamental frequency, that is 2 pi over Ts. That is my fundamental frequency, and k times omega naught becomes. You could maybe it actually even is okay to even change it at this point to omega s, because this we have already defined to be the sampling frequency. So my fundamental frequency is actually my sampling frequency, and so the Fourier series computation, and all of the Fourier series coefficients come out to be 1 over Ts. So, S of t in its Fourier series representation, all the Fourier series coefficients are 1 over Ts summation k equal to minus infinity to infinity e power j k omega s into t. Basically, all of them are complex exponentials, all of them have got the same weight. Just recall that the Fourier transform of e power j omega naught t, Fourier transform of this is 2 pi times delta, Dirac delta of omega minus omega naught, omega minus omega naught. So, basically that tells me that the S of j omega will be 2 pi by Ts, 2 pi coming from the Fourier transform of the complex exponentials, summation k equal to minus infinity to infinity delta of omega minus k omega s, okay, or in other words this can also be written as k times 2 pi by Ts. So, again the S of j omega also is a series of exponentials. I am sure these are well known results. Okay, so the convolution that we need to have, so the property of convolution, if this is my input spectrum x of j omega convolved with a Dirac delta at omega naught, this gives me the following result. It basically shifts the spectrum to the center frequency of the Dirac delta. So, if this is omega b minus omega b, then after convolution it becomes omega naught plus omega b, omega naught minus omega b, okay, and the center frequency. Okay, so that is the basic convolution property. So, expand it now to convolve with not a single impulse, but a train of impulses, each of them amplitude of the impulses 2 pi over Ts, okay, or so these would be at an amplitude of 2 pi over Ts. When I do the convolution, I have there is a 1 over 2 pi. So, the 2 pi gets removed. So, what I am left with is a scale factor of 1 over Ts. So, 1 over Ts is what is present, and what will happen is each of these will get a copy of the x of j omega. Okay. So, this is omega s, this is omega b, this point is omega s minus omega b, this point is omega s plus omega b, exactly using the basic principles that we have talked about. Okay, so, I hope you are clear that the input spectrum, if it had an amplitude of 1, through the process of sampling would have come that, and mathematically the expression is S of j omega, this is the sampled signal, is a product of the two. So, basically it is the xs of j omega. Xs of j omega is equal to 1 over Ts summation k equal to minus infinity to infinity xc of j omega minus k omega s. This is after the convolution, all the shifted copies of the spectrum. a scale factor of 1 over Ts, which is already visible from the graph. So, I would like to just highlight 3 elements from this expression. These are useful for us in our understanding and comfort level with the whole sampling process. First of all, keep in mind that there is a scale factor. Should not ignore it, should not omit it. This is something that we have to be careful, because we are interested in reconstruction. Okay. The second element, very, very important. Basically, we have produced multiple copies of the input spectrum. So, in fact, an infinite number of copies. So, I will just write it as multiple copies of input spectrum. Through the sampling process, this is inevitable. This is of the input signal spectrum, or I will just write it as input spectrum. And these input spectral copies are separated by multiples of the sampling frequency. So, that is multiples of the sampling frequency. And all of these are very important in our study, because we are going to be talking about multiple sampling rates, but at the same time the ability to reconstruct. So, therefore, multiples of the sampling frequency. Okay. So, one interesting observation which we can draw from this diagram. So, observation. Now, what should be the condition that the images do not overlap? What should be the condition that, so basically look at this portion of the spectrum. Omega S minus omega B is the lower edge or the trailing edge, and the leading edge is omega B. If this is greater than, let's keep it strictly greater than, just for is greater than omega B, then there is no overlap. Am I right? And each of those, now you may say, why not you take it for any other of those gaps? You can take it for any gap. Eventually you will find that the condition that it boils down to is that sigma S should be greater than 2 times omega B, right? And this is nothing but the Nyquist criterion. So, the Nyquist criterion actually can be viewed just from the sampling process, it becomes very evident. Now, you may say, why not greater than or equal to? Okay, if you say that it has to be equal to, okay, let me just give you the answer for that as well. That is what actually Nyquist criterion says. Anyone knows why in most of the practical DSP cases we just say, okay, over satisfy the Nyquist criterion, don't stay exactly at Nyquist. Okay, one at a time. Okay, that is one. You have to be very careful about what is the value of the spectrum at that omega B. Okay, any other answer? The filter design. Okay, that's a very important element, because now even from this particular discussion, we can move into the next aspect of our what we wanted to cover is the reconstruction process. So, the sampling process has created the following. Sampling process has created these images. Now, let us say that we have completed whatever task we wanted to do, and now we want to reconstruct the signal. So, this is the sampled signal. This is xs of j omega. Now, the reconstruction process basically requires you to get rid of these images. So, the reconstruction filter is actually a low pass filter which removes all the unwanted images, keeps only the central image. Now, the aspect that was mentioned is that if you had exactly Nyquist criterion, then what you will need is a filter which is a ideal filter, okay, ideal filter, a brick wall filter, okay, and in neither in digital nor in analog are these realizable filters. So, and of course, if it was not 0 at this point, okay, that was another point that was mentioned, okay, if it was not 0, then it adds another dimension to the problem, because if you had a situation where you had something like this, then it's even more tricky when you want to do the reconstruction process, because you want to make sure that your reconstruction filter does not remove any of the information of the signal. Now, when this is the scenario and your filter is also in this drawn in this fashion, okay, what is the frequency response of the filter at the band edge? It's supposed to be 0, because it's a cutoff filter, right? It has to cut off. So, basically you create some issues about the reconstruction at the band edge. So, for one reason or the other, you would want to be careful with the Nyquist criterion. So, I would say that, you know, by and large it's safer for us to over satisfy the Nyquist criterion, satisfy it in a manner that it is easy for us to work with. Okay, let's take a couple of examples which I believe are helpful and instructive, and we will then look at some interesting applications as well. So, everyone comfortable with the statement about the reconstruction process? Okay, everyone is comfortable with that? Okay. And also with the statement about the requirement of the continuous time filter.